Hello scholars, you are welcome to the day 6 of the 2026 JAM and Waec Chemistry Masterclass. So viewers, you are welcome back to the 2026 JAM and Waec Chemistry Masterclass, and this promises to be a comprehensive and interactive session, and I do hope you learn or you get the very best out of this class. So in the course of this class, we are going to look at one very important aspect of chemistry, which is the Iupac nomenclature of organic compounds. And in this video, we are going to take a section out of organic chemistry. So I'm going to look at what we call the Iupac nomenclature of organic compound. So Iupac here, this word Iupac, it stands for what we call the International Union for Pure and Applied Chemistry. So the word Iupac here simply means the International Union for Pure and Applied Chemistry. So that's where you have the word Iupac, PAC. So it's a professional body that regulates how things in chemistry are being done or how certain things are done. So the Iupac nomenclature, now this word nomenclature means name. So Iupac has set a name or a pattern for naming organic compounds. So that pattern is what we are going to look at today. Already, we have what we call an old system of naming. Then the Iupac system is a new system of naming. So we have an old system, and then we have the new system. And that new system is determined by the Iupac system. So in this course of this class, we are going to look at organic compound. And like I said, organic compound is just, or this naming of organic compound is a section of organic chemistry. Because in organic chemistry, there are a lot of things we have to talk about, but we are just going to look at how we can name compounds, just basics of organic chemistry. But before we look at the Iupac nomenclature, we just want to understand something. And what is that thing? We want to understand what organic chemistry is. We just want to look at the broader word or the umbrella word, which is organic chemistry. So how do we define organic chemistry? Organic chemistry is simply defined as the study of carbon and its compound, emphasis on those words. So organic chemistry entails, organic chemistry is the study of carbon and its compound, with certain exceptions, with the exception of I'm going to list them. We have number one, we have what we call the oxides of carbon. Number two, we have what we call the metallic cyanide. Number three, we have what we call the metallic carbides. And number four, we have what we call the trioxocarbonate of metals. So before we look at how to name organic compounds, there are some basic things we want to know. What are these organic compounds? What are they actually? So that's why we are looking at the definition of organic chemistry. Now, organic chemistry is simply defined as the study of carbon and its compound. So in essence, we are looking at the compounds that carbon can form. There are a lot. That is why a special part of chemistry is dedicated to what? Organic chemistry. In that section, we are just looking at the compounds of carbon because they are so numerous. So we are looking at the study of carbon and its compound. But there are certain exceptions in the sense that there are some compounds that have carbon, but you don't study them in organic chemistry. And what are they? Number one, we have what we call the oxides of carbon. And in chemistry, we have those two oxides of carbon. What are those two oxides of carbon? We have what we call carbon 2 oxide, which is CO, and then we have carbon 4 oxide, which is CO2. So in organic chemistry, one of the things we don't study in organic chemistry are the oxides of carbon. So what are the oxides? Oxide just simply means when oxygen is combined with another element. So in this case, when oxygen is combined with carbon, we have carbon oxide. Good examples are the two examples we have, or the two types of oxide of carbon. They are carbon 2 oxide, which is CO, and then carbon 4 oxide, which is CO2. So in organic chemistry, we don't study those two because they are not organic compounds, rather they are inorganic compounds. Also, we don't study what we call the metallic cyanide. Metallic cyanide is simply a metal added to the cyano group. And what is cyano group? The cyano group is what we call CN. So carbon attached to nitrogen with a triple bond. So it's something like this. We have carbon with a triple bond to nitrogen. So this is cyano group. And when a cyano group is joined to a metal, we now have what we call the metallic cyanide. For example, we have NaCN. So this is called sodium cyanide. So this, in this case, this compound contains carbon, but it is not an organic compound. So metallic cyanides are not organic compound, rather they are inorganic compound. Also, we don't study what we call the metallic carbides. Now, for metallic carbides, when metal are joined to carbon, so simply say a metal plus carbon will give us what we call a metallic carbide. For example, we can have something like this CaC. So this is Ca is calcium, C is carbon. So when they are joined together, we form what we call a carbide. So this is calcium carbide. So this compound is not an organic compound, rather it is an inorganic compound. Also, the last exceptions we have are what we call the triazocarbonate of metal. Triazocarbonate of metals are just metal attached to the triazocarbonate 4 ion. And triazocarbonate 4 ion is CO3 2-. So in a case where we have CaCO3, this is a metal attached to the triazocarbonate ion. So this is calcium triazocarbonate 4. So this compound, though it has carbon, it is not an organic compound, rather it's an inorganic compound. So in essence, organic chemistry is simply the study of carbon and its compound with certain exceptions, and those exceptions are the oxide of carbon, the metallic cyanide, the metallic carbide, and lastly the triazocarbonate of metal. So that's basically what organic chemistry is. So just to let you know about something, organic as the word here just simply means life. So initially, organic compounds were thought to be gotten from living things alone. So the belief as at then, before certain inventions and certain experiments, was that you can only get organic compound from living things. But later, certain experiments proved that this compound can also be synthesized by humans in the lab. But though the name still holds as today. So basically, initially it was believed that organic compounds were gotten from living things. But recently, or with modern experiments, they now found that this compound can be synthesized in the lab. But speaking to the fact that we are looking at organic chemistry, it's just a study of carbon and its compound, with exceptions to this exception, oxide of carbon. Don't forget that the metallic cyanide, the metallic carbide, and also the triazocarbonate of metals. So after this, we are just going to look at what we call the uniqueness of carbon. What makes carbon so unique? Why is carbon given a special part called organic chemistry? Why can carbon form a lot of compounds? Well, we are going to look at the uniqueness of carbon, what makes carbon to be distinct. So let's go. So we are going to look at what we call the uniqueness of carbon. So uniqueness of carbon. Uniqueness of carbon. So there are certain uniqueness of carbon. We are going to pick some important ones. Now, the first uniqueness of carbon, what makes carbon so special? It has a special ability. And that ability, we refer to it as the ability to catenate. To catenate. So we refer to that ability as the ability to catenate. Now, what is catenation? Now, catenation is simply the joining of like atoms together. So catenation is the joining of like atoms. The joining of like atoms together. The joining of like atoms together. Now, it's not only, take note of this, it is not only carbon that can catenate. There are other elements that can catenate. Example of elements that can catenate, you have silicon, you have phosphorus. Now, these elements, they can also catenate. But speaking to carbon, carbon has this uniqueness Now it's because of this uniqueness of carbon, that is why it can form many compounds. Now when we talk about catenation, just think of it as one that has this tendency to be social or an extrovert. So when an extrovert or a social person meets like 50 persons, that person has the ability to what? To connect with these different persons. So that's how carbon is. Carbon is just like a very social person, or a social element rather, or an extrovert. So that's why carbon can bond with like atoms, and for that reason carbon can form chains or can form a whole lot of structures. So and it is for that reason that's why carbon can form many compounds, where it can bond to one carbon, a second carbon, a third, a fourth, a fifth, even down to 100 carbon. So that ability to join other atoms of itself is what we refer to as catenation. So we tend to see things like C to C to C to C to C. So this ability is what we refer to as catenation. Now the second ability is that carbon has the ability to form multiple bonds. Ability to form multiple bonds. It has this ability to form what? Multiple bonds. So now you will tend to see things like what we refer to as double bond, triple bond, basically. So you will see that in some compounds you just have the ability to form just a single bond, or maybe some just double bond. Basically, they can form not just single bond, double bond, triple bond. So examples of this multiple bond we are talking about are double bond. You get to see things like what? Triple bond, etc. So we try to see something like carbon with a double bond on that carbon. This is a good example of a double bond. Or we can see carbon with a triple bond on that carbon atom. So this tendency is another uniqueness of carbon. So number 3, carbon exhibits a minimum valency of +2, take note of this, and maximum valency of +4. So it exhibits a minimum valency of +2 and then a maximum valency of +4. Now minimum means the lowest, while maximum means the highest. Now in chemistry, there's what we refer to as the ground state, and then there's what we refer to as the excited state. Now what's the difference? It's just like you have a child that has not eaten. Now this child is so moody and the child stays in one place lonely. Immediately you give this child food, what happens? That child starts jumping. Now that is the same thing that happens to atoms. Now when atoms, they don't have this energy, they will stay in a form we call the ground state. And at the ground state, carbon has a valency of +2, or what we refer to as the minimum valency. So it is at this state that we have what we call carbon 2 oxide, which is CO, or the old name will tell us it is carbon monoxide. So when carbon becomes excited, when it absorbs energy, it now moves from the ground state to an excited state. And that excited state, it will have an higher valency. It now have that tendency to what? To form multiple bonds. So at that form, we have what we call a maximum valency of +4. Maximum, the highest it can attain. So it is at this state we have what we call carbon 4 oxide. Carbon 4 oxide, so which is CO2, or the old name is carbon dioxide, because we have 2 carbon. So take note of this. And lastly, number 4, it has the ability to undergo hybridization. It has the ability to undergo what we call hybridization. It has the ability to undergo what we call hybridization. Now let's explain hybridization. Now hybridization is just like a state. So let me give you a classical example. So in hybridization, or when we talk about hybrid, the animals that I refer to as hybrid animals. Now what hybrid animals? I take this species and I take a different species and I bring them together, and they will form an entirely new organism or an entirely new offspring. So let's say we have 2 dogs. We have the German Shepherd and we have the Rottweiler, and then we bring them together, we cross them. Then they can form a totally new organism or a totally new dog, somehow different from the Rottweiler and somehow different from the German Shepherd. So that organism or that animal is now what we call an hybrid animal. The same thing happens in chemistry. In chemistry, we have what we call hybridization. And what's hybridization? Hybridization is simply the joining of different orbitals together to form a new orbital. So we are joining different, just like it's German Shepherd and Rottweiler. We are joining two different, but in this case, we are joining different orbitals. So we are joining different orbitals to form a new orbital. So in chemistry, we have what we call the SPDF. So we have what we call the SPDF. So this one's the orbital. So there could be a case I could join just one S and one P. And we have what we call the SP hybridization. So there could be a case I could join the S, because S can only be one, then P can be three. So we can have something like, let me take this part off the board. So we can have something, the S can just be one, just one, P can be three, then D can be 5, then F can be 7. So there could be a case I could just take one S and just one P. S and P, they are totally different, and then I bring them together. I'm going to have what we call the SP hybridization. It could also be I take one S and two P. We are going to have what we call the SP2 hybridization. It could also be that I take one S and the 3P. I'm going to have what we call the SP3 hybridization. Or I could take even one S, the 3P, and then one D. Then we could have what we call the SP3D hybridization. So there are a lot of hybridization. So different compounds have different form of hybridization, and you get to know this when you study them one after the other. For example, the alkane, the alkene, the alkyne, and so on and so forth. So these are the units of carbon. So just to go over them, we said that the units of carbon include, number one, the ability to catenate, which means joining of like atoms together. Secondly, we said they have this ability to form what we call multiple bonds. And thirdly, we said they have the ability, or they exhibit a minimum valency of +2 and then a maximum valency of +4. And lastly, they have this unique ability to undergo what we call hybridization. Now, mind you, this ability are not just only unique to carbon, because there are other compounds, or the other compounds we get to see in chemistry that also have these special abilities, but we take them as what we refer to as the uniqueness of carbon. So with this being said, we can now move on to the naming of organic chemistry, of organic compounds proper. But before we do that, there are still some extra things we'll look at. We want to look at what we call functional group, and then we are going to look at what we call the number of carbon atoms. We are going to look at how they are named one after the other. So we are going to look at functional group, we are going to look at homologous series, and then we are going to look at carbon atoms, their numbers, how they are named, or their prefix. So let's go. So the next thing we are going to look at are certain things that will help us to name organic compounds proper. So we'll first look at what we refer to as functional group, and thereafter we're going to look at what we call the homologous series, and last look at the number of carbon atoms, and thereafter we'll now look at the steps for naming organic compounds. So let's go. So we'll start with functional group. So the first look at is functional group. So let me take this part off the board. So let's take the units of carbon. But please don't forget the units of carbon. Like we said, there are just 4. Number 1 is the ability to catenate. Number 2 is the ability to form multiple bonds, which will either be double bond or triple bond. Number 3 is that they exhibit a minimum valency of +2 and a maximum valency of +4. And lastly, we said they have this special ability to undergo what we call hybridization, which means forming of new orbitals or joining of different orbitals to form new orbitals. So let's take a look at the first part of this class, which is functional group. So one key thing we'll keep talking about throughout the course of naming organic compound is what we refer to as functional group. So what is a functional group? Very simple. So a functional group is defined as an atom. So a functional group is an atom. It's an atom. It could be an atom. It could be a group of atoms. Or it could be a bond. Or a bond which is peculiar to a particular homologous series. Which is peculiar to a particular homologous series. So noted. Now there's something that we add. Now what is very important? Note this thing. Note it determines the chemical property. It determines the chemical property or the chemical properties rather of an organic compound. Now let's talk about functional group. What is a functional group? A functional group is an atom. Number one, the first key thing is that a functional group can be an atom. Now you get to see some compounds here we have something like this. We get to see things we call X. X stands for what we call halogens. So this S can be chlorine, this S can be bromine, this S can be fluorine, this S can be iodine, or let's say astatine. So you get to see compounds that contain any of these guys. We call them haloalkanes. So we call this compound haloalkanes. So number one, a functional group can be an atom. There are some compounds that contain just oxygen within it. This compound we call them ethers. Ethers. That's their own name, or the Iupac is what we call them alkane. So you tend to see compounds that have just an atom, and that atom is their functional group. So a functional can be an atom. It can be a group of atom. For example, you see a family that contains what we call OH. Now this OH is a functional group for a family that is called the alkanol. Or you tend to see compound that called this COOH, which is the alkanoic acid, or their other name is the carboxylic acid, the alkanoic acid. So now look at something. This is a group of atoms OH, O and H together. This is a group of atoms COOH together. So it could be an atom, it could be a group of atoms. Or in some cases, it could be a bond. For example, we tend to see things like single bond. So compounds that contain single bond, we call them the alkenes. We tend to see things that have double bond. Things like this, we call them the alkenes. Or there are some that have triple bond, we call them the alkynes. So now that's what a functional group is. So it's an atom, it's a group of atoms, or it can be a bond, and it is so peculiar to a particular homologous series. Now these names I'm writing out: haloalkane, ethers, alkane, alkynes, alkanoic acid, and a whole lot of others. We call them homologous. They are families. So when we talk about homologous series, we are talking about a family. So it is peculiar to a particular family of organic compound. Just like we have families, what's peculiar to a particular family? They are surname. So that's how we know them. So once we give a compound that contains ANE, that's their family. That's an alkane. So there are some that you see they contain a double bond. We just know that this family is what? An alkene. Some contain a triple bond. We know that that's what? An alkyne. So they can be group of atoms or bond, and they are just peculiar to a particular family. There's some family that probably they will just have the tribal marks, or there's something just unique about a particular family. So that unique thing is what we refer to as functional groups. So secondly, or very important, is that the functional group determines the chemical property of every organic compound. It determines the chemical property. Now take note of this, because in your exam, more especially the UTME and the Waec and GC and other related exam, you could be asked this question: the chemical property of an homologous series or of a particular organic compound is determined by what? Your single answer to that question is the functional group. The functional group determines how. When we talk about chemical property, we are talking about how they will react. How will they react with one another? For example, this guy has an OH, this guy has a COH. Because of this COH, this guy behaves like an acid. So just think that's why it's called an alkanic acid. Because of this OH here, this guy behaves like a base. That's why, for this reason, alkanol and then alkanoic acid, they can react to form what we call esters. So they can react. So it tells us how can they react, or how, just like somebody's name now, there's a name of a person which is called XYZ. XYZ. And it's another family that has its own name, ABC. And these two families, they are in good terms. They can marry. A child from here and a child from here can get married. But if one has been offended, or there is this enmity between this family and this family, and then you come and tell the parents that, ABC tells his or her parents that, I want to get married to someone from XYZ, they'll be like, no, we are not going to get married to them. So it's just the family name. So that's what functional group determines. Functional group determines how this compound they will react. That's what we talk about. That's what we mean by their chemical properties. So the next thing we are going to look at is what we call homologous series. But before we look at that, we'll first look at what we call the number of carbon atoms, prefix for the number of carbon atoms. So let's go. So the second thing we just want to look at is the prefix for the number of carbon atoms. Because it's very important. You cannot name an organic compound without counting number of carbon atoms. So the second thing we look at is the prefix. The prefix for the number of carbon atoms. So we are going to look at the prefix for a number of carbon atoms. Now let's look at this prefix. Now, what's the prefix? In English language, prefix is defined as anything you add before a word. So something you add before a word. So if, for example, we have nutrition as a word, nutrition. The word we can add before nutrition is mal, M-A-L. So M-A-L is a prefix. So I'm going to have what we call malnutrition. Simple. So any word you just tend to add before another word is what we call a prefix. Or, for example, we have appropriate. Then we can add the word misappropriate. Simple. So any word you add is what we call prefix. So the same thing for number of carbon atoms, we give them what we call a prefix. So now let's take a good look at this. Now for number of carbon atoms, we'll start from 1 carbon atom, 2 carbon atom. So for 1 carbon atom, for 1 carbon atom, we use the prefix met, M-E-T-H. Then for a 2 carbon atom, we use the prefix called what? Et. For a 3 carbon atom, we use the prefix called prop. That's why you get things like what we call propane, because it contains a 3 carbon atom. Then for a 4 carbon atom, we use the prefix called but or but. For a 5 carbon atom, we use the prefix called pent. Then for a 6 carbon atom, we use the prefix called hex. Then for a 7 carbon atom, we use the prefix called hex. Then for the 8 carbon atom, we use the prefix called oct. Now, thinking of the 8 carbon atom, there's an animal that is called the octopus. And why is it called the octopus? Because it has 8 legs. So whenever you count the number of carbon atoms, and you get to see that it's an 8 carbon atom, just remember the animal, octopus. Then for 9 carbon atoms, we refer to this as a non. And for a 10 carbon atom structure, we call it a deck. Now, mind you, we just listed 10, but it could be more than 10. But basically, for our exams, it's ideal we know between the first carbon atom and the 10th carbon atom. So from the first carbon atom again, we refer to it as met. For the second carbon atom, we refer to it as et. For the third, we refer to it as a prop. For the fourth, boot. 5, pent. 6, hex. Hept. 7 is the hept. 8 is oct. 9 is non, and 10 is deck. For those of us that have done polygon in mathematics, I think we will find this relevant. There are shapes that are called pentagon because they have 5 sides, hexagon because they have 6 sides, heptagon because they have 7 sides, octagon because they have 8 sides, nonagon because they have 10 sides, and then decagon because, sorry, nonagon because it has 9 sides, and then decagon because it has 10 sides. So it's just very important, even beyond chemistry. So that's very important. So the last thing we look at is what we call the homologous series. So this is the very important thing we are going to look at. And then in our second part of this class, in our next class, tomorrow, we are then going to look at all the various steps, how to name, how to draw. So that's what tomorrow class is going to be centered on. So let's start homologous series. So let's take a good look at homologous series. So let's go. So we are going to take a look at, then the last thing we are going to look at in today's class is what we call the homologous. When we talk about functional group, and I said homologous series, they are families. So just like we are in the world today, there are a lot of human beings, billions of human beings in the world today. Now it will be very hard if we don't name them. So that's why we have the system of naming. So if you go to a particular place and say that you are looking for ABC, probably they will use ABC. Or I go to a place and say I'm looking for Martins John, they'll say, oh, this is Martins John. Or Ojo Peter, they'll tell that this is Ojo Peter. So that is why the system of naming is very important. And family. So with family, you can easily trace a person. So that's the sense of the homologous series we are going to look at. So homologous series, they are families. Because one of the unique things of carbon is that carbon has a lot of compounds. So this compound, there are so many. So to easily study them and to easily understand them, they've placed them in families, certain different families. And those families are what we refer to as homologous series. So in essence, homologous series is a family of organic compound, a family of organic compound, in which each successive member differ by a CH2 group, and 14 grams. So that's basically what an homologous series is. Now let's understand something. Now for the homologous series, like we say, it's a family, and so like I told you, there are a lot of compounds, there are a lot of organic compounds. So to easily understand them, they place them in families. So if you look at this compound, oh, it has this property, let's place it here. If probably they all have single bond, you can place them in one family. If they have double bond, there's a family you can place them. If they have triple bond, so just like that. So that's the family of organic compound. Now each successive member is also referred to as an homolog. So you get to see this word called homolog. So each of those members is also referred to as what? An homolog. So just like we have a class. Now each member of that class, we can call them a pupil or a student. Or let's say, for example, we have a team, a football team. Each member can call them a player. So now each member of a family is what we refer to as an homolog. Now that homolog, they differ by what we call a CH2 group and a 14-gram mass. Now let me explain these two parts, this CH2 group and then this 14-gram mass. Now very important, I will give you a family. One of the family is an alkane. So alkane is an homologous series. So under alkane, we have various members, like we have the methane, we have ethane, we have what we call propane. So these guys, they are members of alkane. So alkane is a family. So these are the members. There are a lot of them, but let's put this three. Now methane is CH4, ethane is C2H6, propane is C3H8. So these guys, they are families. Now what do we mean? We say each successive means they follow each other. So ethane follows methane, propane follows ethane. So now differ here means the difference. So if you look at the difference, this has one carbon. The difference between 2 and 1 is 1. So the difference is 1 carbon. Now 6 minus 4 is 2. That's like H2. If you also do between these two, the difference between propane and ethane, 3 minus 2 is 1. Now 8 minus 6, you keep getting ethane is C2H4, propane is C3H6, butane is C4H8. Now if you take the difference between these two, 3 minus 2 is 1 again. Now 4 minus 6 is 2. So difference again is CH2. The same thing we apply here. 4 minus 3 is 1, then 8 minus 6 is 2. Now you get to see that the difference between each successive member is a CH2 group. Now what about the 14 gram mass? It's just the difference between their mass. Now if you calculate for this one, you are going to get a mass of, that's 12 plus 4, that's about 16 gram. Then for this one, you are going to get a mass of 30 gram. And for this one, you're going to get a mass of 44 gram. Now, if you subtract 30 minus 16, you're going to get 14. When you calculate the molar mass, you end up getting this one. So now, 30 minus 16 will give us 14. Also, 44 minus 30 will also give us 14. So now, an homologous series is just a family. Now, each member, just like we have children, we can say, oh, if they gave us a first child in 2000, the next child in 2002, the next child in 2004. So the difference in their age would be 2 years. So the same thing happens here. Now, each member of the family, the difference between them is a CH2 group and a 14, not all, and 14 gram. So take note of that. So that's homologous series. So the next thing we are going to look at is that we are going to look at a list of all the homologous series we have in chemistry. But before we do that, I'll just add something to the note I gave to you on the number of carbon atom. We said the number of carbon atom ranges from 1 carbon atom and beyond. So for 1, we talk about met. For 2, we talk about earth. For 3, we talk about prop. For 4, we talk about boot. For 5, we talk about pen. 6 earth, 7 earth, 8 oct, 9 non, and 10 tech. And we can go beyond that. Now, something very important I didn't add is that the number of carbon atom determines the physical property. Remember, the functional group determines the chemical property, while the number of carbon atoms determines the physical property. So take note of that. So the functional group of a particular compound will determine its chemical property, meaning how it will react. Then the number of carbon atoms will not determine the physical property. A good example is that if you look at this family, okay, I'll list this family for you. For example, this alkane. So for alkane, we have methane, ethane, propane, we have butane, we have pentane, we have hexane, we have heptane, we have octane, so on and so forth. Now, methane has 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5, 6, 7, 8. Now, if you look at this first four compounds of alkane, in terms of their physical property, you tend to see that they are what? Gases. Now, if you come down to the next four, you tend to see that they are what we call volatile liquids. So as you keep coming down, their physical property keep changing, just like their state of matter. It could also be their boiling point. You see that probably this could be 40 degrees Celsius. As you move down, this could be 40.5 degrees Celsius. You can have 41 degrees Celsius, 42. So that physical property, because boiling point and melting point, they are physical property. So you keep seeing these changes. So now take note of that. The number of carbon atoms will determine the physical property of an organic compound, while the functional will determine the chemical property of that organic compound. So it is worth knowing. So after now, I will just go back to the comment section. If you have any question, any suggestion, please do have to leave them in the comment section of this live stream. I'll go back to the video and check if there are any questions, and then thereafter I'll come back to give you a table which shows us the various homologous series we have in chemistry. So in the comment section, someone asked about what we call neopentane. Though this class, we are not going to focus on neopentane, but I will just tell us what neopentane is. So we are going to look at what neopentane is. So now let's go. So we are going to look at neopentane, and thereafter I'm going to give us a table which contains the various homologous series we have in chemistry. So the person asked about neopentane. Neopentane. Now what's pentane? Just like we said, pentane. Pent here means 5. Now the N here tells us that it belongs to the alkene, and the alkene have, so it belongs to the alkene. And one unique thing about the alkenes that they have what called single bond. Single bond. So that's just the what do you call it? The pentane. So pentane, when you draw pentane, pentane should be something like this. Pentane is just something like this. So we have H, we have H, we have H, we have H right here. We have H, 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 and then we have H. So this is pentane. Now pentane can be in so many, like it can exist in so many forms. That's where the topic we call isomerism now comes in. Now isomerism just means existence of a compound in the same molecular formula but different structural formula. Means just I can be like this with my hands straight. I'm still myself with 2 hands, 2 legs, 2 ears and whatever. And myself, I can do like this. Now this is a different structure, different from this structure. I'm still myself, but I'm taking different structure like this, like this. I could act like this, I could act like this. Now, so what I just did just now is isomerism. So same molecular formula but different structural formula. That's what referred to as isomerism. So pentane can be in different isomers. So there are so many isomers. But the real pentane is what we just refer to as a neopentane. Some people say a normal, some people write as N-pentane, which is like normal pentane. Pentane can also be in this form. Now look at this form. Look at this form. So this is another form. If you count, you see that we have 1, 2, 3, 4, 5. 5 carbon atoms again. Pent. All single bond. So this is a structure that looks like pentane, but we don't call it pentane. Though we can call it what we call isopentane, meaning an isomer of pentane. But then the real name for this compound, we'll call it a 2,2-dimethyl propane. Dimethylpropane. But though we get to look at this in our subsequent class, that's in our next class, where we are going to complete the whole concept of naming of organic compound. But now what you get to see that they are just 5, they are both 5 carbon atoms. Just like this is normal pentane, and then this is an isomer of pentane. So I hope I've answered your question. So if you have any other question, any comment or any suggestion, just go to leave them in the comment section. And when I go behind the camera, I'll get to see your question and also answer them. So now let's come back to homologous series. So let's take homologous series. Homologous series. So let's go. So I'm going to draw a table, and the table is going to be all encompassing, and that will form the basis for us to name compounds in our subsequent class. So now we're going to look at this table. So we have a table. So let me take that in a better form. So we have, I'm going to take this table. So in this table we have what we call homologous series. So on this side we have what we call the homologous series. Or let me take that down a bit. Please permit me to take this off the board again. So we have homologous series. Homologous series. So from homologous series, we are going to take what we call their functional group. And thereafter, we just take what we call their general molecular formula. So if you are still on this class, do it to draw a table like this in your book, and when you are done the class, try and go over the various homologous series. try and know their functional group and then their general molecular formula. Because in exam, you could be asked this: general molecular formula of alkene, or general molecular formula of alkene, or general molecular formula of alkyne, or any other family we are going to talk about today. Now let's start with the basic, or the simplest homologous series, which we call alkane. So that we call alkane. Now the function of the alkane does include the single bond. Single bond. So once you see a compound, all single bonds, start thinking of alkane. Now the general molecular formula for the alkane we refer to it as the CnH2n plus 2. So that is the general molecular formula for the alkane. The CnH2n plus 2. So number 2, we are going to look at what we call the alkene. Now we refer to the alkene as the family that have what we call double bond. So this guy, so single bond, this just a single bond, a good example. So for this we have what we call the double bond. Double bond. So you get to see something like an equal to, which is double bond. And the general molecular formula, which they could ask you in exam, is CnH2n. Then for the third one, we have what we call the alkyne. For the alkyne, they have what we call the triple bond. And you see these 3 slash, or that 3 horizontal line, which is like the equivalent sign. So that's the triple bond. And the general molecular formula is CnH2n minus 2. So we have that. Then next we are going to look at what we call the alkanol. Now for any family I give you from number 4, I'll tell you their Iupac name, which is alkanol. Their old name, or they are previously called alcohol, though they are still referred to as alcohol, but their Iupac name is also referred to as alkanol. Now alkanol, their formula is called the OH. OH. So you see a compound that has OH, that's the hydroxy group. Start thinking of the alkanol. Now for the alkanol, the general molecular formula is CnH2n plus 1 OH. This is a plus 1 OH. Now I'm going to tell you something very, very important, which is I will talk to you about it on this part of the board. We call it an alkyl. Alkyl. So what's an alkyl? An alkyl is simply an alkane that has lost one hydrogen. So alkyl is just simply is a compound formed when an alkane. So think of this: an alkane loses an hydrogen atom. So loses an hydrogen atom is our next keyword. So you get different marker. So now when an alkane loses an hydrogen atom, we refer to that compound formed as an alkene. Now let me show you something. A good example of an alkane is, we call it methane. Methane. And methane is CH4. So let me just write by the side. CH4. So we have CH4. So when this methane loses one hydrogen, means that we are going to remove one hydrogen from this H. So we are going to have what we call a methyl. Now methyl is going to be a CH3. In some groups, we'll put a minus to tell us that something is missing. So methane becomes methyl. So look at it, ANE, that's methane. KYL, methyl. So YL rather, methyl. So similarly, we can have what we call ethane. Ethane is C2H6. So when this guy loses one hydrogen, so out of 6, if it loses one, it's going to be 5. So now we're going to have what we call ethyl. Ethyl is going to be C2H5, no longer 6. So this ethyl. So similarly, we can have propane. So we can have propane. So if propane loses one hydrogen, it's no longer going to be called propane, but rather we're going to call it a propyl. So take note of these differences. So whenever an alkane loses an hydrogen, it is referred to as an alkyl. Now, mind you, alkyl is represented with what we call arrow. Arrow. So whenever you see arrow, just know that you are talking about an alkyl. An alkyl is, so now look at something. An alkane is CnH2n plus 1. So an alkane is Cn rather, H2n plus 2. So if we remove 1, this is going to be a CnH2n plus 1, because an alkane will lose 1 hydrogen to become alkyl. So that's why you see this guy, CnH2n plus 1. These are an alkyl. So in some books, you get to see it written as arrow, because everything here stands for an alkyl. Arrow OH. So just the same thing. So whenever you see arrow, know they are talking about an alkyl. So Cn H2n plus 1 OH, or is in a simple form ROH. So let's move on. Because at some point we are no longer going to write Cn H2n plus 1. Right? We just write ROH. So you should know that the arrow is an alkyl. And an alkyl is a compound formed when an alkene loses an hydrogen atom. So let's move on. So the next compound we are going to look at is what we call the alkanoic acid. Number 5, we have what we call the alkanoic acid. So their old name, they were previously called the carboxylic. They were previously called the carboxylic acid. Now for these guys, they are formula with COOH. Now in our second class tomorrow, we are going to talk about how to expand these structures. Because there are ways, because it's one thing to know how to draw a compound, it's another thing to know how to also name the compound. So you should also name when they give you the structure, and when they give you the name, you should also be able to draw. So the two of them go side by side. So you see COH. So the general molecular formula is just simply arrow COOH. Already, we've established the fact for what an arrow is, and an arrow is simply an alkyl. So that's arrow COOH. So the third one we are going to look at, we call them the ethers. So not the ethers, rather. We call them the alkoxyalkene. Alkoxyalkene. So I'm going to just clean up this part. Alkoxyalkene. So this is their Iupac name. So their old name, they are previously called ethers. So their functional group is the oxygen atom. So this oxygen atom. So you get to see things like arrow, O, arrow. So that's for the ester. So I'll take one more, then I'll go behind the camera and check if there are any questions. So number 7, we have what we call the esters. So we have what we call not the esters, because their Iupac name is not esters. The Iupac name is alkanoids. So their old name is what we call esters, but not the ester you know as a person. Is the ester without an H and with an S at the back. So this is the CO. So for this is arrow, COO. So this is the arrow COO arrow. So we have this compound, we have listed 7, but there are more than 7. So when I go behind the screen, I'll check for questions, comment, or any suggestions, and thereafter I'll return back to the board to complete this table. But mind you, like I told you, we have these families, we have their functional group, and if you remember, I said functional group are atoms. They are, for example, this is an atom, they are group of atom, or they are bonds that are peculiar to every particular homologous series. Now, something about each homologous series I didn't tell you before is that every homologous series have what we call a general molecular formula. Take note of that. So I will say the general molecular formula for these 7 homologous families, or these homologous series I've been to you. And one other thing I told you about is that they have what we call an arrow. An arrow here stands for an alkene. An alkene is basically a alkene that has lost an hydrogen. So let me check for any questions, comment, or suggestions. So if you have any, please go ahead to drop them in the comment section so that I can quickly attend to them. So in the absence of any question or any comment or suggestion, we are going to move on. So we've listed a whole lot of homologous series. We've looked at alkane, we looked at alkene, alkyne, alkanol, we are previously called alcohol, alkanoic acid, we are previously called carboxylic acid, oxyalkane, and we are previously called the ethers. We have looked at the alkanoid, which we are previously called the ester. So we are going to add more to this table. So let's move on. So let's take a look at more families. So the eighth one we are going to look at, we call them, they are what we call the alkanal. And their old name, they are previously called the aldehyde. Aldehyde. Now, some friends in PG will say aldehyde. So they are called the aldehyde. Now their functional group is the CHO. That's CHO functional group. Now, so the ideal molecular formula is the ROCHO. Already we've established the fact that RO here is an alkyl. So take note of that, that's an alkyl. So we have that. Then number 9, we have what we call the alkanon. Alkanon. So take note of their functional group, because you cannot name any compound if you don't know the functional group. Imagine they give you a compound, for example, that has something like this, then an OH here. If you don't know that this is alkanol, there's no way you can name this compound. Well, it's a very simple thing. I'm just going to count number of carbon atom 1, 2, 3. So 3 is what? A prop. So prop. Then this the alkanol, adds the suffix anol. So you've named the compound the propanol with all the hydrogen included. So take note of that. So it is very, very important to know the various functional group of each of the family. So now let's move on. Then number 9, we have the alkanon. And for the alkanon, they are old, or they were previously called ketones. Ketone. Now this is the CO. So you get to see common like ROCO. So in this case, there are two different alkyl group. So that's the alkanon. Then number 10, we're going to add what we call the haloalkane. Alkane. So it is the X. Now this X can be anything. Now S can be chlorine, S can be bromine, S can be fluorine. X here stands for halogen. Take note of that. So this X here stands for the halogen. It can be bromine, it can be iodine, it can be astatine. So that's what X stands for. Then you see come out that is what ROX. So this is what we call haloalkane. So it's simple. Halogen to form an alkane. That's why they call haloalkane. So we have an ROX. Then the next we look at what we call the amine. Amine. So for the amine, they have what we call the nitrile group. So let's just take this as okay, let's go. So they have just the N. And so we have this as the N, okay. So N, now this N, or let's take it in this format. N, okay, the NH2 rather, sorry. So we have this as NH2, okay, better put, because the N is the nitrile. So that's the NH2. So then, this group is called, take note, this group is called the amino group. The amino group. So now we do something like RONH2. So this is an amine, or something can say the amine. And there's something unique about the amine. The amine have what we call fishy smell, like they have this smell of fish, as fishy smell. Then the 12th one we have to look at what we call the amide. The amide. Now the amide have CO plus this NH2. CO plus NH2. So you get to see them like the ROCONH2. So you see a compound that has CONH2. You start thinking of the amide. Now the amide is also called the secondary amine. So let's just add that to their name. So they also called the secondary amine. Secondary amine. So they are just like a bigger form of this amine because amine have NH2. These guys have CO NH2. So we call them the secondary amine. So number 13, we'll just take our very last one. Our very last one I'm going to look at is the nitrine. Nitrine. So for a nitrine, it's just carbon triple bonded to nitrogen. So this group you call it the cyano group. The cyano group. So you get to see this like ROCN. So this is what we call the nitride. So we'll name compound later. One name they will call them propanonitride, butanonitride. So this nitride are these compounds that have this cyano group. You see double bonded to nitrogen. So you will see them like this ROCN. So basically these are the common homologous series we ought to know for the purpose of our exam. So we've looked at them from alkane down to the nitride. So take note of this. And in our next class, we are going to look at the steps for naming organic compounds. So we are going to name different compounds across different families. And that's how we are going to apply it. So if you have any question, any comment or suggestion, please do it to leave them in the comment section of this video. And if you are watching this video, you just came across this video for the very first time, don't forget to click on the subscribe button and also turn on the notification bell so that whenever I release any video, you always get notified. And please, for those of us that have challenges, you can always go to drop your challenging topic in the comment section of any video. I always get notified and then I'll look at that topic as a video and always upload them. So for the rest of the day, do it to enjoy the rest of your evening. Goodbye, and also do have a wonderful Christmas celebration and a prosperous 2026.